All right. How well we can see this, well, who knows. I have this posted for the course. We're going to talk about bonding in molecules. So we finished the quantum mechanical model. This chart is actually a pretty good idea. First time using it, I didn't bother typing it, just left it in handwriting. So you can break this into two categories. The quantum mechanical model versus the non-quantum mechanical model. So over here, and I can draw a couple of quick examples for this, non-quantum models. So the Bohr-Rutherford diagram. So a classic example of this one would be, I don't know, H2O. So the Bohr-Rutherford diagram would say start with oxygen, which has a +8 nucleus, and then you draw these circular sort of orbit type diagrams. The first one, you're allowed to put 2 electrons in. The next one, and you have to fill them in at 12, 3, 6, 9. So we got 1, 2, 6, 7, 8. So this would be oxygen. And then we have 2 hydrogens. So one of the things they even start demonstrating in, I don't know if it's grade 10 or whatever, you have oxygen, which is a +1 nucleus, and then it has its first ring. And I'll draw a little triangular dot for the electron that arguably came from that one. Then you have your other one. So there you go. The Bohr-Rutherford diagram that shows an example of bonding. So you can see how this is sort of even a precursor for the Lewis theory, where you count up all your valence electrons, which is your outer ring. The inner ones are left untouched, was part of their idea. But the dots. So Lewis theory, I'm not going to bother going through counting up all the electrons, but for instance, H2O, one of the classic sort of diagrams would be something like this, right? So that is a Lewis. So I want to make one thing clear. The procedure to get here is what I'm going to say for myself personally is horrible. And there's some debate, but I think it should go. The notation is good. So notation is nothing more than the idea of drawing dots for electrons and sticks for bonds. Notation good. Procedure how to get here using the official counting of electrons, no good. So that's just my opinion. That's how we're going to teach it. So that covers this area of the chart. So next up on this side, squish this over, quantum mechanical model. Well, under that we've got two things. The valence bond theory is a theory that, as you'll see, has quite a few assumptions and hybridization and orbital overlap still in play versus the real quantum treatment. And there's various degrees of this real quantum treatment. One of them is the very idea of, in textbooks, even your first year textbook says if you have a powerful enough computer with the right software, you could arguably draw a structure such as methane, right, in ChemDraw or something like that, and then you can have this computer go through what they call numerical mathematical analysis, which I'm not that familiar with. When you use the word numerical analysis, there's quite a few varieties of how you can do it. You can do even the SCF model that they came up with for the atom and orbitals used numerical analysis to get there. But in the world of bonding, there's a whole bunch of these. Molecular orbital theory, whether they use some hybridization. The funny thing is the hybridization doesn't actually exist. So let me just show you what real quantum treatment at the heart and soul of it really is. So we recall when we were talking about an atom all by itself, okay? You could have a hydrogen proton, and we take an electron that looks like a little BB in our hand, and we're going to throw it in the system. If it goes to the ground state, we come to find out through a lot of pain and agony, for instance, the electron takes on the shape of a 1s orbital. So we have what's like a box or a containment. The spherical nucleus keeps the negative electron around it. It spreads itself out. We even talked about our energy level diagram, right? Well, that kind of went in there. So let's do it this way, 1s, 2s, 2p. If we give this more energy and it was to change its shape to that of a p orbital. So we have these energy states and we have electron density picture. So it's the one thing quantum mechanics does, and it does very well. It's the one thing numerical analysis of any, but this, what was the container here? The container was that. Okay, so what if we moved on to, what if we held 2 protons at a distance that happened to be the same as a hydrogen bond distance? Throw 1 electron in. Well, guess what's going to happen? This is now a different box, cage, holding 1 electron. In the system you get is a hydrogen atom with 1. So you're still going to have energy states. And this one would have 1 electron, then you could throw another one in, and it would pair up, and it'd be in the ground state, call it energy level number 1, 2, 3. They're not going to be able to use, you know, S, P, and D things for this. But what quantum mechanics and student software now in second university can do is you can give them a molecule such as this. The quantum treatment will do exactly what we already seen for particle in the box, the solutions for this, but it can do it numerically, and it can generate 2 things. Energy spacings of the allowable energy states this system can have, and the shapes. Each one of these energy states has its own characteristic electron configuration for the molecule. We call this a molecular orbital. So does everybody see in the future when you can talk to a computer and you can draw in ChemDraw a structure such as this and say, go ahead. Okay, just had to take a quick break there. People coming in saying who you talking to. It's the camera. So, atom. Isn't it funny how even high school books talk quite clearly about the idea of these orbitals, which remember how I said in quantum mechanics. Number 1, you can calculate energy states, ping, 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 and the differences. And number 2, the electron density shapes, and those are what we call orbitals. And notice how this doesn't care if the box, the containment, the boundary condition, the system is a simple singular atom with the allowable energy states and shape of the orbital, or if it's an actual molecule, such as the simplest one, 2 hydrogen nuclei and the electron density around it, that's a molecular orbital. They're the same thing quantum gives us. This one's obviously more complicated. We don't have as nice an organizational system as SP and D orbitals that we can build into, right? But the exact same procedure is what it is. So that's crucial, and that right here is what the real quantum treatment is. So for instance, if they were going to do it on methane, one thing you could do is you could say, look, we already know the bond lengths. So let's say that we used lasers in a vacuum or something like that, and we positioned the hydrogens in a tetrahedral arrangement, but there's no electrons in the system. So the real quantum treatment, just like an atom says, instead of that being our box, just the carbon nucleus, now we have 5 total positive things creating the trap, the cage, the box, the boundary condition. So you take 1 electron, throw it in here, and they can actually calculate and show experimentally how 1 electron in this bare bones system, and I don't know exactly what, but let's just say you're going to get some kind of image of electron density, however it shapes out. And they're going to calculate the allowable energy states, and each state, so the first one goes in, the second, then the third, you might get different anti-bonding type electron densities, but they can get pictures of them for each of the states. That's the real quantum treatment. Now, the better job you want to do of this, and the more complicated the atom gets, the more computer power and time it takes to do the numerical analysis. I mean, you could go rent time on one of the latest and greatest, maybe new Watson computers to do that for you. But they can build into this lower levels of numerical analysis, bigger assumptions, but they can give you approximate pictures of the electron density and energy differences, which is pretty useful. So, 25, 30 years from now, you might have, just like your calculator now, The first calculators in the 80s had a hard time doing the quadratic formula, for instance. You had to pay extra money for that. So in the future, your little handheld cell phone might be able to do this when you say, you just talk to it, okay, draw me methane's molecular orbitals. Okay, that's real quantum treatment. We still can't do that, and we still have to, especially in organic. So for organic, for instance, you're going to draw that, and maybe we'll put in an aldehyde. Then we could say, draw us the orbitals that are used to build this. So you could even focus on this. So what's going to happen is you say, here's carbon. It's going to be sp. It's got 3 sticks. It's going to have 3 sp2 orbitals. The hydrogen will do this. This carbon will use one of its orbitals to overlap, right? And then this one is going to, oxygen is also sp2, but then each of them uses its remaining p orbital to overlap this way. So does everybody see how in organic, when we talk about this in all the textbooks, you still have to be able to talk about this? This is the type of valence bond, well defined and still used, especially for organic and single bonded things. This type of imagery is what we have to talk about and be able to do. So we're going to have to cover some hybridization. We're going to have to talk about geometry, bond lengths, and stuff like that. So that's what we're going to end up working for. And that's why we need it. So, valence bond theory. I will first go down this route, well defined and still used. I just briefly showed you organic molecules, but we're going to go over here, which is the standard starting point, single bonded molecules, okay? Giving us those infamous shapes. We'll talk about electronic geometry, we'll talk about the molecular geometry, what the difference is, teeter-totters, T-shaped and all that. So that's where we're going to start. And for that, I might have to zoom in here because the font on this print, let me back out right there, and I'll just read it. So the general notes for well-defined valence bond theory. So yet again, to locate us on the chart, valence bond theory, well-defined, single bond. This is what we're covering first. That's what this is. These are in your notes, posted on Blackboard. Valence bond theory, molecules of single bonds. The classic high school and first year bonding molecules, such as, for example, SF6. And we all know that SF6, you end up with something that arguably looks like this. And we'll call it octahedral geometry. We'll talk about the bond angles and all that. These ones are going back. These ones are coming out. So the single-sticked, classic geometry bonding type thing. So these are the rules of how to make this thing work, and there's 5 of them. First one, each bond or stick is going to be made of an unpaired electron from both atoms of the bond. So for instance, if you had, I'm trying to think here. If you, if you had this, hydrogen, that's a molecule. This represents a stick in a drawing, and we know that each stick, each one, and if I label this one as hydrogen A and hydrogen B, I could redraw this, right? I'll stretch it out a bit. This one brought its own electron. This one brought its own electron. They're sharing it. So every stick is made of each atom bringing an unpaired electron. So that's bring your own electron is the idea to the bonding or social situation these two atoms hook up to. The other way you could look at it is, right, here's hydrogen A in a 1s orbital. Here's hydrogen B in a 1s orbital, right? See how they're showing they're unpaired? So this tells me how many, because if you draw this picture, how many bonds could this hydrogen make? Well, this rule says every single bond needs an unpaired electron. Well, it has one and it's unpaired, so it makes one stick. And then we could say, how are we going to show this bonding take place? Well, you could say, let's just say that you have a +1 nucleus of your hydrogen. You can even draw H. And you could draw an s orbital and the other one s orbital and say they each did overlap. So the concept of atomic orbital overlap is a crucial idea for this conventional valence bond model. Okay? I'll make some statements at the end of this. You have to use valence electrons for bonding only. What does that mean? I think we know it. You could take this table, right? And for instance, what if somebody says, let's look at selenium. Well, selenium's in the 2, 3, 4 p block, right? It has 1, 2, 3, 4 electrons in the 4 p block. So back it up, skip the d orbitals, you get the 4s, and then it goes back to argon. Well, argon is the closed configuration, so we ignore all the electrons and orbitals before that. All we look at is the 4s and the 4p for selenium. So if I was going to do selenium as my atom of interest, I'm only going to look at its valence. And in this bonding model, you ignore the D as well. So this would be the 4s and the 4p. And we know that the 4s for selenium is filled, and it looks like that. So use valence, and this is the energy level diagram, and this would be selenium by itself. We start from the by itself electron configuration or energy level diagram. Number 3, pretend the d electrons are not used in bonding at all, hence why all high school and first year chem books do not have any like this in them. So you're not going to have transition metal type bonding questions, right? There's a different model that you learn later in inorganic, etc., for types of bonding or interactions when you involve transition metals, right? So our focus for the starting point one is S and P block type things, right? And I think we already, this example, selenium was a perfect one. We talked about that. So now we're moving on to this rule. Draw the central atom in an energy level diagram, which we already showed with selenium in its valence. This is by itself. Then the other atoms approach it. When the other atoms approach it, try to envision the central atom reconfiguring the electron density of the orbitals, redoing itself or hybridizing itself so as to make hybrid orbitals, and at the same time enough unpaired electrons to make the necessary number of bonds. Circle the orbitals required to achieve this and redraw the energy level diagram with these hybrid orbitals. So let's go back to selenium. This is selenium by itself, minding its own business, right? By itself. So let's say somebody says, make selenium difluoride. Well, this is where somebody's going to say, well, look, it already has 2 unpaired electrons. But the one thing that you're going to learn about is anytime you have a central atom, well, obviously we're going to automatically treat the 2 halogens as external around the central atom selenium. Look, it already could do this because we know that fluorine, for instance, right, with Lewis dot notation will have an unpaired electron. So the 2 fluorines could already be willing to bond to this. But note, folks, if the selenium was to stay this configuration, the 2 p orbitals, which are 90 degrees to each other, bonding to this, the bond angle would be 90 degrees, and that's not what's experimentally observed. So the hybridization model was used to prepare us for regions of electron density. We'll talk about that in a second. So what we're going to do is say, look, the 4D does exist, and it says circle the appropriate number of orbitals needed, and as long as the principal quantum number is there, you can do it. Remember, though, as a footnote, the 2s and the 2p, there is no such thing, 1, 2, 3, 4, 5, there's no such thing as 2 d orbitals. See, so therefore, the only things you could ever circle are just these 4 orbitals. That's why the 2p block cannot expand past 4 sticks. Whereas selenium has access to this if you want them. So I could circle more if I wanted. But we already know for this fluorine, we only have 2 of them. We only need 2 unpaired electrons. So we could circle this. And what you do, how many orbitals did I just circle? 1, 2, 3, 4. 1, 2, 3, 4. We made 4 sp3 orbitals. And all hybrid orbitals look pretty much like this, where they have a tail and most of their electron density is here. That's a standard. Why did we call them sp3? Because I circled 3 p orbitals and 1 s orbital. How many electrons did I circle within this? And the key word here is write down the words. This is the selenium now starting to acknowledge fluorines are coming. So instead of being totally by itself like an atom, it's going to reconfigure itself. okay? Hybridize itself, reconfigure, making, instead of 3 p's and 1 s, making these 4 equivalent sp3 orbitals. There's energy of stability, and they'll say things all like that, but you have 6 electrons. 1, 2, 3, 4, 5, 6. Now you have setting up for the geometry in a second. So fluorine, we can write like that. We know fluorine already has 1 unpaired. We don't normally, you can, folks. You're going to see mixtures of this. We took the time to hybridize the central atom like this. In truth, we know that even the fluorine atom itself is going to probably be close to this sp3 as well. It's not going to stay. The last electron in fluorine was a 2p, and it looked like this. So that when fluorine is by itself, the unpaired electron is in a p orbital. So technically this electron could be a p orbital, but even this will hybridize itself. But the outlying atoms like this, we just ignore them normally, okay? So don't panic if you see sometimes they try to hybridize this one too, others don't. All you need to know, it has a 1 unpaired electron, so we're going to make a bond. And this fluorine will do the same. Okay? Now, number 5, and we'll show it on this. Number 5 says each lone pair or bond is considered a region of electron density, ROEG, and it gets put into one of the following geometry drawings. So the fundamental geometry drawings for regions of electron density. If I have you get some sort of central atom, and you get 2 other things. This is called linear. Imagine that. So I don't know. Just call it a central atom, right? And you got 2 things on the outside. You know, let's say this is 180 degrees. Ooh. What if you have 3 regions? Central atom A, 120, and this is called trigonal planar. What if I have 4 regions of electron density? The sticks that are drawn normal like this mean it's in the plane of the page. The dashed line means that stick is going behind the page. The wedge means it's coming out. So in other words, if I was standing at a chalkboard, these are normally in the board, but these 2 would be like your 2 fingers in a board going like this, where one of them is behind the board and the other one is coming out at you when you hold your 2 fingers like that. This is tetrahedral. Tetrahedral. And in a perfectly symmetrical one, these are 109 degrees. And the reason the tetra comes from the fact that when you have a tetrahedron, it has 4, see these 1, 2, 3, triangular faces. Has 4 of them, hence tetra. What if I have 5 regions of electron density? Well, for that, what you're going to have is this, and it's going to be called trigonal bipyramidal. 5 items, your central atoms here. This is interesting because these here are like this in one plane, right? These are called equatorial sticks, axial. If I was something in the axial position, do you see I'm going to have a 90-degree angle with 1, 2, 3 sticks. The equatorial ones, one of them only makes 90 degrees with 2 other sticks. The others are 120. So if you're a larger thing getting bonded to something, there's more room in the equatorial positions. And then if there's 6 regions of electron density, what you're going to get is octahedral. Octahedral. Because if you look, 1, 2, 3, that's 1 triangular face. 1, 2, 3, the second. 1, 2, 3, the third in the back is 4. 4 on the bottom, 4 on the top, octa. 8 triangular faces of that geometry. These are the 6 shapes. Now, I mean, there is a 7th one, you know, but they're going to call that pentagonal. This one's a little hard for me to draw. You're going to have almost like a pentagon, right? So you need 5 sticks. This is called pentagonal bipyramidal. This one's rare, and if I'm not mistaken, I think it's like iodine in the center and 7 chlorines or something like that. So you have 5 in the middle plane, and then 2 on the top, 1 on the top and the bottom. Pentagonal. That one's rare, but the rest of these are very common. So let's go back to this one. Regions of electron density. Which shape do we pick? Well, count with me. It doesn't care if it's a lone pair of electrons or if it's an actual bond. 1, 2, 3, 4. 4 regions of electron density. You go to this one automatically. And then you simply fill in the sticks. I got 2 fluorines, so I can put those here. And then 2 lone pairs. Now the lone pairs we normally draw a little like balloon figurey. That is our tetrahedral, and that's electronic geometry. Electronic geometry means how many regions of electron density? 4, therefore tetrahedral, because the electron density puts itself as far apart as possible, which is tetrahedral. Electronic geometry is tetrahedral. But then we do something that I don't like, and it's called molecular geometry. And this is where we kind of joked about in class. I said, it's like the bullying or the hazing of people in real life where you pretend or you snobby, you pretend somebody's not there, you're not looking at it. Well, they're saying pretend that these lone pairs don't exist. I know it's kind of harsh. If you're looking at that molecule as if those lone pairs are not there, what does that look like to you? It looks like a bent. So this would be called bent. I don't like it. This one is superior because this whole analysis, and it shows you everything, both atoms and lone pairs. This one is a little gimmicky, right? But you get like a half a mark for that on your test just so that you remembered it or whatever. This is the process, and we're going to start taking you through a whole host of general classes to finish just one classification of valence bond theory. This is probably the best and most well defined by rules of this procedure. When we move on to organic molecules, we'll use this procedure but slightly a bit looser, and then we'll move into some stuff that's really loose using it, but we'll adapt it, right? So we have that. So we could start, let's see, first example could be for instance, beryllium. So let's look at some examples. 2 regions of electron density. Okay. Well, I'm thinking that for this one, you're pretty much, you're going to have beryllium. I think beryllium is it. You could have beryllium H2, beryllium X2, where those are the halogens. Fluorine, chlorine, bromine, iodine. Okay, so beryllium is sort of the go-to thing. The issue is this, folks, and you have to memorize this. You do have to memorize this a little bit. Somebody could say, well, how come you can't go down below and treat magnesium the same? Beryllium's kind of funny. Even though beryllium, like for instance lithium, sodium, potassium, rubidium, they all react very much the same way. They like to give up an electron and be like a positive ion. Beryllium does not. This one's sort of special in its own sense because the 2s orbital perhaps is filled, energy, stability, you name it. So we can't treat magnesium like it's like beryllium. But what we can do is treat magnesium, calcium, strontium, barium. These behave very much the same. These behave the same, but beryllium is a little bit of a class all on its own. So this is like almost like a special case, but it demonstrates what we're going to do. So, I don't know, let's do example beryllium iodide. Well, right away you're going to say we always take this as a central atom. We always draw a picture of it when it was by itself. And there's the 2s, there's the 2p. 2 Ds, 1, 2, 3, 4, 5, do not exist. Don't make that mistake. So this is beryllium by itself, minding its own business, and it looks like that. Now, listen carefully. If somebody tells me this exists, you're telling me that 2 iodines come to bond it. So right away, you can almost tell right away that it's going to have to look like this. I mean, what else can you do? You have to draw sticks. You're telling me this is the single bond, single stick model. So right away, can I just draw this? Well, we know it's going to be this, but we know that every single stick is made up of 1 unpaired electron from each of them. So the first thing you think about is iodine electron configuration Lewis dot looks like that. Do you see how there's an unpaired electron? So iodines are already ready to go. But this beryllium configured this way, are there any unpaired electrons at this moment? No, they're paired. So if beryllium stays configured this way, it's not bonding anything. So this is that thing we said to envision as the iodines come closer, that this says, you know what, I'm going to reconfigure myself. So somebody could say, how do you know you're only going to circle these two and say these two orbitals hybridize, or reconfigure? Well, think of it this way. If I had circled all four and I hybridize them, 1, 2, 3, 4, how many electrons can I put in here? 1, 2. Do I really need these two? So it's almost like you're saying, I only have 2 electrons. I know that I only want to make 2 unpaired electrons. So I've circled 2 orbitals, therefore in the energy ranking, somewhere in between these two, I'll put the 2 new sp hybrid orbitals. And they're going to look like this. And these 2 p's stay there for housekeeping purposes, and it looks like that. So now along comes iodine. It has 1 unpaired electron, so we can do this. You draw in your Lewis dots just to make it look good, and then you say to yourself, okay, we've made the linkages. How many regions of electron density? 1, 2. 2 regions of electron density. Therefore, we have no choice but to say, here's beryllium. We're going to have to do linear, and it'll be fluorine. Just like this. Linear, 180. So what we've done here is essentially draw the Lewis structure, with sticks and dots. Okay, but what if somebody says, I want you to show me the hybrid orbitals and all atomic orbital overlaps? Well, beryllium has these 2 orbitals, and the thing about these is these hybrid orbitals are going to be equal in energy, okay? They're all going to look the same. I don't care if it's sp, sp2, sp3. They're essentially, for drawing purposes, we're not doing the exact calculations. They look like this, and this area is going to point at the atom it wants to bond with. We've already relied on the shape. Remember how I said you'd have the atom and you'd have 2 lines? So our atom is beryllium and the 2 ends are fluorine. So you fill in the shape that you know it is. So you're going to have fluorine. Now, what you can do with fluorine is, I'm okay with saying, look, not fluorine, iodine. That was iodine, my bad. Getting tired. So there's iodine. Some people will say that that's actually let's count it, 2, 3, 4, 5p orbital unpaired electron, if it was by itself. But folks, in a bonding world, you can just say, look, iodine almost for sure is going to hybridize some way, shape, or form to get overlap just like that. I don't need to draw the rest of the stuff on the iodine, but what I do have to do is draw the rest of the electron dots, like I did here, right? And then on the other side, beryllium puts out another sp2. Iodine does sort of the same thing in reverse. And that's what we get. The other electrons are there. That's it. So then the electronic geometry equals the molecular geometry here, which equals linear. No differences. There's no lone pairs here, so that's going to sit like that, and we're good. So that is okay. We've done 2 regions. So what's the next one? 3 regions of electron density. So for this, we've already talked about the automatic shape is I'm going to have some generic atom in the middle, and it's going to do that. If I have an example of something like that. So the examples I can have of that one, I mean, you're looking at things like BH3, BX3, aluminum H3, aluminum X3, go down to gallium H3, gallium X3. You could probably even get away with indium as well. So the point is, strangely enough, you go boron, aluminum, gallium, and indium, and we're starting to get the picture that in the single stick atom molecular model, H's and X's are the things we like to stick to the central atom. So I don't know, why don't I pick pick one of these. So let's say my example is going to be aluminum trichloride. Popular one, every single textbook's going to have one like this, and you're supposed to draw the stick diagram. We already know we're going to go towards that, but let's go through the analysis. Aluminum. So aluminum, this is the 2p block. This is aluminum is in the 3p, 2s back there, 3s. So when aluminum is by itself, you've got 3s, 3p. And aluminum has 3 electrons, 1, 2, 3. So right away we're looking at this when aluminum's by itself. It has 1 unpaired electron, where we can clearly see the first rule of the process says, what number of sticks are you going to have to make single sticked 3 chlorines on aluminum? Well, you need 3 sticks. You need 3 unpaired electrons on the aluminum itself waiting to make those number of bonds. So aluminum configured this way by itself is not going to fly. So right away you have 3 electrons, so you're thinking if I had 3 orbitals that I'm going to hybridize, I'll get 1 in each. So reconfigure, hybridize, reconfigure. Now you're going to get 1, 2, I've circled 3 orbitals, an s, 2 p's, 3 orbitals, so you're going to get 3 sp2s. And they do look approximately like this. And they will point themselves directly at what they're bonding with. That remaining 3p is going to be there, hypothetically for housekeeping purposes, but without an electron actually in it, it's not really there. But 3 electrons is what you have. And we already know that chlorine by itself, 1, 2, 3, 4, 5, 6, 7, and usually I write the unpaired electron like that. So we have 3 chlorines, each of them using its unpaired electron. Lewis dot these up. This shows 1, 2, 3 regions of electron density. Put themselves as far apart as possible means you're going to get your central atom aluminum. So this is aluminum on this side, hybrid. And it's going to have 3 sticks. You have your chlorines. Da-dot, da-dot, da-dot. And this is 120 degrees. So that is an acceptable Lewis drawing or structure with some geometry already indicated. They might call that Vesper or some other name like that. But the point is, what we're illustrating, and these shapes are because the electron densities want to push themselves as far apart as possible, which is 120. If I'm supposed to draw examples of the bonding, I can still draw the lines in, but then I draw in the hybrid orbitals. Now, I'll forget the tails for this because it's just on the other side. You could draw them in if you want, but it gets messy. So the 3 sp2 hybrid orbitals on aluminum look like this, and then the chlorine is essentially going to do the same thing itself. Make an sp3 orbital in its case to overlap like that. So these are the atomic orbitals, if you want, hybridized, to show the overlap and bonding situation that creates that geometry. And this is called, in this case, we have no lone pairs. Electric geometry equals the molecular geometry, which equals trigonal planar. Right? Trigonal planar. So that's another analysis showing us example of 3 regions. So now we can move on to 4. So what I'm going to do is, I'm not going to build this up slowly. Some books are going to take you through one at a time. If you have all 4 regions of electron density are atoms, and then it moves on to 3 atoms, 1 lone pair, 2 atoms, 2 lone pairs, 1 atom, 3 lone pairs, right? So what I can do is just show you a mixture, and the analysis is going to take care of itself, which is kind of nice. In fact, it's very nice. So what if I was to draw you know, the classic H2O, you could have methane, oxygen's there. What else do we got? Ammonia. We could drop down. You could have SH2. You could have under there silicon, right? And then under there phosphorus, H3. But the truth is, these are all H's around a central atom, but you could just as usually put in X's. So, thought experiment for X's. What if somebody had Br2O? So do you see how we switched out the H for X's? And this could be done across all these, arguably, certainly on paper, right? These are interesting scenarios. And I think, well, you could even have HX, right? You could have XX. So what if you had chlorine, chlorine, and this was H chlorine, right? So you see the pattern that's building up here. This one for 4 regions has 4 atoms. You could go 3 atoms, 1 lone pair, 2 atoms, 2 lone pairs, 1 atom, 3 lone pairs. But all in all, you still have 4 regions of electron density around the central atom. So we could start with the classic water, right? Water is a very popular one. So you always start with oxygen by itself, as if nothing was around, 2S, 2P, and oxygen looks like that. Oxygen by itself. Now, we know darn well that hydrogens are coming into to bond. So we know that we're going to need 2 sticks, 2 unpaired electrons. Well, we already have it, but we already know that when the bonding takes place, these are not going to stay this way, because energetically, we're told, quantum mechanically, this isn't going to fly. This atom is going to reconfigure itself, or more correctly put, the molecule, the new box, which is 2 hydrogens and an oxygen, nuclei. That new box is going to make the electron configure itself in the molecule differently than when one atom is by itself. But this is the wording, and it turns out this one is going to circle all 4. So you're going to hybridize, you're going to reconfigure itself, the oxygen will, and you'll get 1, 2, 3, 4. 4 sp 3 orbitals. Each one of them looks pretty much the same as any hybrid orbital, just like that. 6 electrons have to go into the 4 equivalent hybrid orbitals, okay, which produce that. And now, we already know that hydrogen has 1 unpaired electron. So each hydrogen can pull into these docking stations of unpaired electrons on the hybridized oxygen, right? So 1, 2, 3, 4 regions of electron density. And our chart already told us that you have to draw a tetrahedral template like this, and we say our central atom is oxygen in this case. Where can you put the electrons? Where can you put the hydrogens? It doesn't really matter, but by convention, it makes it a little easier sometimes to see. They might put the H's here, and then the 2 lone pairs that we had here, 2 lone pairs, get drawn in on 2 of the sticks of the tetrahedral. Now, a perfect symmetrical tetrahedron, the bond angles are 109 point something, or 104.9, or some damn thing like that. Very close. 109, yeah. But lone pairs, okay, they tend to take up a little bit more room. So when you have 2 of them taking up more room, these 2 sticks are going to get ever so slightly squished together. And you have to memorize it. It's less than 109. And if I'm not mistaken, it's like, what, 105-ish? I couldn't care less, as long as on the test you knew that this was going to get tightened up a little bit, less than 109, because of the lone pair needing a little more room, and even quantum mechanics seems to show this, and observations, experimental observations show that that's the case. So if you're going to draw the energy overlap diagram, I would still draw in my template of the tetrahedron, but I would say I've got 4 of these sp3s, and if I have hydrogens here, overlap, 1s orbital overlap, and then these ones just have the lone pair, looks like that. And now we would say, I'm going to use this diagram for the geometry. The electronic geometry is tetrahedral, but the molecular geometry, this is where we become snobs. We cover up and ignore as if it doesn't exist the lone pairs. Wow, that looks bent. It's not linear. You have a bent molecule. Right? This is the better one to focus on because you're looking at everything. So that takes care of water, but we could look at, for another example, ammonia is a good one, which is the same as phosphine. I believe it's phosphine. And then we could look at one of those. So let's do the analysis of the classic ammonia. That's a Lewis little sort of, we show the extra lone pair there. But the analysis is start with the nitrogen, 2s, and I'll try and do this faster. That's 2p. 1, 2, 3, 4, 5. Nitrogen by itself. Well, we need 3. Well, it already has 3. Do we have to hybridize it? The answer is, in any bonding situation in this model, you should automatically go ahead and hybridize it. The larger number of equal, energetically spaced, symmetrical orbitals, that's the model we're using, so we're going to hybridize that. You write down, hybridize, reconfigure, 4 orbitals, 1, 2, 3, 4, the same number of electrons, hydrogens line up like that. 1, 2, 3, 4 regions of electron density, therefore the tetrahedral geometry is what we have to use. I'm going to put the hydrogens on the bottom just because the lone pair I'll put here. 1, 2, 3, 1, 2, 3. And again, if it was totally symmetrical, 109, but this one takes up a little more room, so this will be just slightly less than 109. So I don't know if this one was like 107 or something like that. Slightly squished in because of the lone pair. And that was nitrogen. So now we got to name it. We already know that the electronic geometry is tetrahedral. But the molecular geometry, where we pretend we don't see this, it looks like a pyramid, and the base is 1, 2, 3. So this is a trigonal pyramidal for molecular geometry. If you wanted to show the bond overlap, you would draw your tetrahedron again. You draw your hybrid orbitals like this, the lone pair. If I'm using hydrogen, I show the 1s overlap like that. We're done with that one. So now we move on to, oh, I don't know, what if we had HBr, right? Well, out of the two, they're going to do hybridizing. The bromine's going to do it. So you're going to have bromine is sitting in the 2p, 3p, 4p. Bromine is 4s, 4p, and this is bromine by itself. Bromine looks like that. We know by now that we're going to have to hybridize this. Now, does this one have access to 4d? It does. But do we need to circle more orbitals than is here? And the answer is no, because all we need is 1 unpaired electron, so we could do this. Hybridize. 1, 2, 3, 4. This is bromine. Hybridized. You're going to get 4 sp3s. They all look like that. 1, 2, 3, 4, 5, 6, 7. And hydrogen does that. How many regions of electron density? This is for the geometry and shape. 1, 2, 3, 4. So guess what? Tetrahedral. Again, it doesn't matter. I could put it anywhere. We should always show the lone pairs like this. So the electronic geometry, tetrahedral, molecular geometry, cover all these up. You see two atoms, it's going to be linear. That's it. And that was bromine in the middle. And again, you could do the same trick for showing your orbitals. Draw the tetrahedron. You show all of the hybrid orbitals. Hydrogen would overlap. This gets the dots. Like that. So we're good with that. Alright, so now we're back on... Let me just see where I'm at here. A little better. Now we're on to five regions of electron density. I don't know why I keep putting G there, but anyway. Regions of electron density. We already know that you're going to get a shape trigonal bipyramidal for 5 regions of electron density. It doesn't matter if you have atoms or lone pairs. If you have 5 regions like that, this is what it will be. So there's a variety of things, whether you have lone pairs or not. So a couple, I would just list a few classic examples. You can have that. You can have SF4. You can have, I don't know, chlorine with 3 fluorines. Xenon with 2. So when you look at this, it doesn't look like any obvious automatic, makes sense reason. And then if you're looking at phosphorus, to get 5 sticks, you can't use the 2p block. So even though nitrogen's above it, we know that these ones can only make 4 sticks. But under phosphorus, you have, you got arsenic or antimony. You go to sulfur, it could be selenium or tellurium, do the same thing. And then xenon is down here. Xenon is low enough down that they can make some bonds sometimes. Krypton, I don't know if they'll show that too much. But you can see how when you go down, and then of course chlorine with 3 fluorines, you could have bromine with the 3 fluorines. You get a bromine with 3 chlorines. You can mix and match. So this is not all encompassing. This is meant to demonstrate what you can do. So let's do these 4, and I'll try and make it shorter and save some paper here. PCl5. As always, P is in the 3p block, so you're going to have 1, 2, 3. You're going to have the 3s, the 3p. This is phosphorus by itself. 1, 2, 3, 4, 5, and you need 5 sticks, but we know we need more than just 4. If I circle these and get 4 orbitals, I'm still going to have 3 unpaired electrons. 1, 2, 3, 4, 5. The 3d, and you need the principal quantum numbers to be the same. Otherwise, that's another little rule. You're not allowed to circle more of a 3 type. So think of it. If I circled this one in the mix, 1, 2, 3, 4, 5 orbitals with 5 electrons, so that will work. So this is what it's going to do. It's going to hybridize. It's going to reconfigure. And you'll get 1, 2, 3, 4, 5 orbitals. 1, 2, 3, 4, 5 sp3d orbitals. And guess what? They're all going to look the same as always, like that. And these 5 electrons, 1, 2, 3, 4, 5. And in this case, we're doing chlorines. We already know that each chlorine has an unpaired electron. 1, 2, 3, 4, 5, 6. And yes, you got to draw these in just to keep track of your electrons. Count regions of electron density around our newly configured phosphorus. 1, 2, 3, 4, 5. So therefore, you have no choice but to do this template. And all you have to do now is say my central thing is phosphorus, and I have that. And yes, folks, you draw in. You're supposed to draw all your electrons. We know that these, and you have to show this on your test, these are 120, these are equatorial, these are the axial sticks, this is 90 degrees. This is called trigonal, electronic geometry, trigonal, by pyramidal, pyramidal. The molecular geometry equals the same thing because there's no lone pairs. To show the same bonding, you would draw the same diagram, but this time you would show pictures of your hybrid orbitals. And then each chlorine would also have its own hybrid orbital overlapping. So remember in this model, now first of all, I'm going to take a little moment here. I don't know if I said it in the video, but quantum mechanics in your first year book, we all know one thing is true. Hybrid orbitals don't actually exist, folks. I already went over in the chart. The only real thing that happens is, in this situation, the nuclei of the chlorines and the phosphorus make out essentially what the new box or containment trap for electrons is. When you put electrons in, they distribute themselves out in molecular orbital fashion. That's it. There is no such thing as orbital overlap. There is no such thing as hybrid orbitals. And there's a nice page and a half right up in your first year book of Zumdahl. Does a great job talking about that. This is a conventional model that we use so that we can talk about things like this on paper. A lot of the characteristics of the real existing molecular orbitals do have a lot in common with this orbital overlap type of thing. But it's a convention you have to learn how to adopt and use. Just like an ideal gas equation is not a perfect way to calculate pressures and temperatures and all that thing, because real gases are different, depending on which one as well. But we use the ideal gas as a model because it makes a lot of our things, generally, we can talk about them very well. Same thing with this. So now we can move on to SF4. So here we go. 1, 2, 3. You get 3S, 3P. 1, 2, 3, 4, 5, 6. This is sulfur by itself. And 1, 2, 3, 4, 5. You have the 3D. I need 4 sticks. So you're going to have to take one of those. You hybridize it. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6 electrons. Sulfur now. 4 fluorines. I'm going to omit drawing the dots to save time, although you would have to do that for all of them. Lone pair, that's 1, 2, 3, 4, 5 regions of electron density, means you have to go with this. And you know one thing, the equatorial sticks versus axial. This is sulfur. A lone pair takes up more room. So therefore, the axial position is not as good, because if you put a bigger object here, it's going to have 1, 2, 3, 90-degree interactions with 3 other things. If I put it equatorial, it's only going to have 2 90-degree. This one's 120. So the lone pair by convention, this is you can put it either here, 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 it doesn't matter. But a lot of times they'll put it here for effect to see the shape. Then they put the fluorines in here. Now, what's interesting, folks, is in reality, this takes a little more room. Do you honestly think this is a perfect 180-degree straight line? Probably not in real life. Maybe it's a 1 degree out. But you know what? This diagram is fine. So the electronic geometry is trigonal bipyramidal. But the molecular geometry, when we get snobby and we pretend that doesn't exist, like it's not there, this is that stupid one that looks like a little teeter-totter, right? Teeter-totter, or they call it seesaw or some damn thing like that. It's almost like this, right? Anyway, that's how you would name that. And again, anytime you draw one of these, you could show sulfur. You show that fluorine would also have overlap. That has that overlap. That, and then fluorine would have overlap. Right? You get the idea. So now we move on to ClF3. Trying to show you how we get through this. It's been a long day, and I'm sure you guys have been there many times studying or working or whatever it is you do. You get tired, you get a little giddy, who knows. Well, 3 fluorines, we're going to assume chlorine. Now chlorine is sitting in a 3p, 3s. Valence has 1 unpaired electron, but 1, 2, 3, 4, 5, 3 Ds are there. This is chlorine by itself. I need to make 3 sticks. 3 unpaired electrons are needed. I only have 1 at the moment. This is going to reconfigure itself in the model we're using. If I do that, hybridize 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and you have 1, 2, 3, 4, 5, 6. 7 electrons. And you got fluorines. 1, 2, 3, 4, 5 regions of electron density. Therefore, you draw this template of the 5-stick figure, which is trigonal bipyramidal. And we say, okay, equatorial sites. Now I'm purposely going to put the lone pairs over here just so it's easier to see the shape. 2 lone pairs, done, equatorial. Fluorines remaining here. Electronic geometry is trigonal. Bipyramidal. Molecular geometry, where we forget these don't exist. Man, that looks like a T. T-shaped, right? And again, I'm not going to do it any longer, but you know how you could draw in the hybrid orbitals on the central chlorine, right? So we've done that. We have one more, xenon. So xenon F2. So xenon is sitting down at 2p, 3p, 4p, 5p. So xenon 5p. What comes after 5p? 5d. 5d exists, 5p, 5s. This is xenon by itself. 1, 2, 3, 4, 5, 6, 7, 8. Totally full, noble gas configuration. We need 2 sticks. So if we circle in one of these, it's going to reconfigure or hybridize itself. You're going to get 1, 2, 3, 4, 5. And you're going to get 1, 2, 3, 4, 5, 6, 7, 8. 2 fluorines. Do that. 1, 2, 3, 4, 5 regions of electron density. You draw this trigonal bipyramidal template. We're dealing with xenon, put that in the middle. Well, lone pairs, they're telling us the equatorial sites give the most room for lone pairs. Therefore, your 2 fluorines will go here. And yes, you're supposed to put these around it. So this electronic geometry is trigonal bipyramidal. But the molecular geometry, when you hide these, looks straight. So they call it linear. We've done yet another one. Wow. So now what do we move on to? Well, octahedral. So now we move on to 6 regions of electron density. And for that we have numerous examples. We could go with SF6. We could go with BRF5. We could do xenon F4. These will demonstrate some classic examples, so let's try and shoehorn these in. Same analysis, we're doing it again. Sulfur, sulfur sitting in. See, I'm getting tired looking at this, but that's normal. 2p, that's 3p. So for sulfur analysis, I'd go ding. It's the 3p, 3s, 1, 2, 3, 4, 5, 3ds. Sulfur, when it's by itself, is going to look like this. 3ds. I need 6 sticks. Look at how many electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I need 6 orbitals total. So I'll circle 6. Say that it hybridized, it found itself, it reconfigured itself, who knows. 1, 2, 3, 4, 5, 6. You're going to make 6 sp3d2s. Okay? Quick note, in all these analysis that I started speeding up on, when you do this, you're supposed to write in 5 sp3ds. This one, 6 regions, sp3d2s. How many d orbitals, how many p's, how many s's? Now, we're sulfur. 1, 2, 3, 4, 5, 6. And fluorines that come in, it's going to go like this. This was sulfur that was hybridized on this side of the fence. Those are the fluorines. And the shape. The shape is very much octahedral template. You know that the central atom is sulfur. You're going to write in your fluorines. And you're going to have to write how all these are 90 degrees, and even this is 90 degrees. Put in all your dots when you do it. Electronic geometry, octahedral. Molecular geometry is the same thing, because there's no lone pairs here for us to ignore. I'll show one of these that if I would draw the same thing like this, I would show the hybrid orbitals reaching out, ready to bond. Fluorine would do the same. Fluorine would have the same. Fluorine. All of these atomic orbitals overlapping to make the bond. That looks to me like we've completed the analysis, the geometries, the hybridization. That's what the molecule looks like. BRF5. So BRF5. So bromine is sitting in 2, 3, 4p. So you've got 4s, 4p, 4d, 1, 2, 3, 4, 5, 6, 7. I need 5 sticks. So it's going to circle 2 of those, 6 orbitals, 1, 2, 3, 4, 5, 6. 6 sp3d2s. And this is bromine all reconfigured. 5, so 7, 1, 2, 3, 4, 5, 6, 7, and then fluorines goes like this. How many regions of electron density? 1, 2, 3, 4, 5, 6. Therefore, the template is octahedral. Bromine is in the middle. These are all identical, all 90 degrees, so the lone pair doesn't matter where you really put it. So why don't I put it on the bottom just so it's easier for us to ignore it later on and mention what we're seeing. You put the fluorines in, and the electronic geometry is octahedral. The molecular geometry, cover this up. Square base goes to a pyramid, so this is called square pyramidal. We're done. Next one. We're speeding this up a bit just to get through it, not to draw it out too much, but xenon. Xenon, again, we already did it earlier. It was 5, 2, 3, 4, 5, yes. So you've got 5s, 5p, 5d, and it is all full, looks like that, needs 4 sticks. If it does that, you get 1, 2, 3, 4, 5, 6. You get 6 sp3d2s. This is xenon, all reconfigured. 1, 2, 3, 4, 5, 6, 7, 8. You get fluorines, right? 1, 2, 3, 4, 5, 6 regions of electron density. Therefore, the shape, 2 lone pairs. Why don't I put one on the top, and why don't I put one on the bottom? And you're left with 4. Electronic geometry is octahedral. Molecular geometry, when you're not looking at these, is square, flat plane, square planar. And I think last but not least, I'll show you a couple tricks here. We'll finish this video. I'm wondering what day it is. We had 7 regions of electron density, which was, you got to draw a pentagon, right? We'll draw a better picture of that in a moment, but one example for that, IF7. Central atom's iodine, which is 1. You've got 5? 2, 3, 4, 5. 5s, 5p, 5d. 1, 2, 3, 4, 5, 6, 7. 7 sticks. I got 7 electrons, so I'm going to need 7 orbitals. So we're going to hybridize this. This is iodine that was by itself originally. 1, 2, 3, 4, 5, 6, 7. So you're going to have 7 sp3d3s. 1, 2, 3, 4, 5, 6, 7. And then fluorine. Fluorine will do this. 7 regions of electron density. So we're going to go 1, 2, 3, 4, 5. It's sort of in a plane, pentagonally around it, right? And this is going to be called pentagonal bipyramidal, and that's the electronic geometry. That's kind of a rare one. So there's a few things that we can do here. One thing I'm going to talk about is, let's just look at chlorine. So if I'm chlorine, how many sticks can I possibly make? Well, if I hybridize this, 1, 2, 3, 4, I can make 1. So example, HCl. If I was to grab one of those, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, I can make 3 sticks. So you could have that. If I was to do that, grab another one, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. So I could go ClF5, right? Number of sticks, 1 stick. This one would have 3 sticks, like, right? So somebody would draw it like that. But we already know that this one would be based on, we already know it's based on that. This one has 6 total, so it's going to be based on octahedral. And then what if it did this? 1, 2, 3, 4, 5, 6, 7. You could do ClF7. This analysis shows you the number of bonds chlorine could hypothetically make, the number of sticks. 1, 3, 5, 7. So is anybody surprised how chlorine for perchlorate, we're going to show you something different than this model we've been doing, but in terms of number of sticks, we already know that chlorine can go up to 7 sticks, it can do 5. So one of the cheats of this is you do this for, we're not looking at geometry when we do oxyacids, but the first step, and we'll show you this, is 1 stick to start for each oxygen. Then draw on the number of negatives you have. Any remaining oxygens get double sticked. How many sticks total for chlorine? 1, 2, 3, 4, 5, 6, 7. How's that possible? Because it can do this hybridization. We're not going to get into the exact geometry of this. This is one of those less well-defined oxyacid methods. But what we did take advantage of is we labeled how many unpaired electrons, thus how many sticks I can draw on paper can chlorine do. That's an interesting thing. We could turn around and do this to sulfur. So if I'm going to do sulfur, sulfur has 3s, 3p, 3d. Sulfur looks like this. If sulfur does this hybridization, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 2 sticks. So sulfur could, if it's this hybridization, but what if it reaches out and does that? 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, 4 sticks. So it can do 2 sticks, it can do 4, and what if it did that? 1, 2, 3, 4, 5, 6, 2, 4, 6 sticks. So that's why sulfur can have something like H2S, it can be SF4, it can be SF6, commonly. So this analysis quickly gives us a look at that, and not too bad. The other thing I'm now going to look at is something like NH4 plus. Okay. Oh my God, how do we do this? Start with nitrogen, 1, 2s, 2p. Nitrogen starts out like this by itself. 4 hydrogens tells me we need 4 sticks. It can only do this anyway, so we're going to hybridize and do 1, 2, 3, 4, sp, 3. Okay? Nitrogen, sp3 hybridized. But there's a positive here. So what you're going to get used to in practicing this is you're going to say, doesn't it make sense that what if this electron, 1, 2, 3, 4, what if that one electron right there was taken out? Well, doesn't this nitrogen now have lost 1 electron? And let's say that what it lost it to was a proton. So that electron was given to this, which became H dot. So now we could call it this. 4 regions of electron density makes it tetrahedral NH plus. Tetrahedral looks like that. See the analysis, it's tricky. So you stop here for a moment and you say, look, I need a positive charge. What does it make sense? Who's going to lose 1 electron? And because they're hydrogens, it makes sense that 1 proton somehow was given that electron, if you will. The other way of looking at this would be if you had N, remember the ammonia that looked like this? Tetrahedral, a lone pair. What if H plus was coming by? So a mechanism later is going to say that's going to go after it. But what you make ends up becoming that hydrogen occupies that site. And remember how we said in a stick, as soon as you make a stick, 1 electron goes to each of them. But see how it started both of them with nitrogen? So now that ownership of one of these electrons that used to be for nitrogen is now over here. This one lost 1 electron, hence the positive 1 charge. So that's how you could handle that. We could go the other way. You might have something negative. I mean, what if you had, oh, I don't know. What would be like negative? OH negative. Well, now you're thinking, hey, wait a minute. Isn't that like this? Isn't it almost like these 2 electrons stay here? So this one originally had 2 other lone pairs, right? Now it's going to take these 2. That one used to belong to that hydrogen. Now it's, so let's make it a triangle just to show it. So now you're going to be left with the H plus proton in this now has acquired an extra one. 4 regions of electron density. We know where this is going. 1, 2, 3. So if you're oxygen by itself, 1, 2, 3, 4, 5, 6, 2p, 2s. Let's hybridize it. 1, 2, 3, 4. Bink, 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 bink. So now we're saying, wait a minute. This is telling me the oxygen is going to gain another electron. We can draw this one in this way, and then the other one can come from a hydrogen. So see, that's the negative extra electron. So you're still going to be tetrahedron. You're only going to have 1 H, and then the others are going to be lone pairs and oxygen. And then one of them has to have a negative charge, if you will. But it doesn't matter which of these 3 it is, but that's the quick analysis that lets you handle using this negatives and positives like we did for ammonia. So ends for this video for now. Valence bond theory, single bond molecules. So I'll end it there and we'll move on to oxyacids probably. I might do these next and save organic for last. We'll see.